Hey everybody, welcome back. So we are ready for module 9 of multivariate statistics. And in this module, we're going to be talking about exploratory factor analysis, or as it's perhaps more commonly known, EFA. EFA, this is a term that gets used a lot in our literature. So this is a incredibly useful technique for trying to see if you have a group of items usually from a survey or some sort of scale that hangs together as a coherent latent construct. So, if you have a set of 10 items that you think all measure the same thing, the same latent construct, EFA is often a good first step in sort of saying, in broad strokes, is that actually the case? And it is an exploratory method, typically done before something like confirmatory factor analysis, which imposes quite a few other kind of restrictions on the model and the type of latent variable that you have. So anyway, EFA is a really good and useful technique to know. It's one that comes up a lot. It's even one that sometimes pops up in people's dissertations, which is fun to see. So I'm going to start my timer here to just be aware of how long I'm going. So I have the R Markdown file, the RMD file for this week, Module 9, up and ready. And I have pointed my RStudio desktop to my place where the data are stored, which is week 9 for me. So we're going to do several things in this video. I think it's probably going to be a multi-parter. The first thing we're going to do is just kind of get comfortable with working with items as part of a scale and calculating coefficient alpha, also known as Cronbach's alpha, which is kind of a very basic initial first estimate of internal consistency and reliability for what we think might be a latent construct. So I'm going to load in the psych package, which we've used quite often before, as well as the tidyverse. And most of the tools that we're going to use today actually come from psych. This is a really excellent package for psychometrics and scale development and validation, and has lots of tools for EFA, which is really nice. And then I'm going to load in the data. And so this is, again, using the Haven package. And the name of this data set is SAQ. So you might see this before. So I, for some reason, have a disconnect between my my R Markdown file and my working directory in my main file, which has already been set to week 9. But you can see the file itself has a working directory. So I can either change that, or I can just copy this and paste it into the command viewer down here into the console, as opposed to running it from the file, and then it loads it in just fine. So that's a little trick you may find sometimes, that you get the same thing. There's a little disconnect there. And then we're going to view this data set called SAQ. So SAQ stands for Statistics Anxiety Questionnaire. And this is data from chapter 17, I think, of Andy Field's excellent book, Statistics with SPSS. I think he has a similar version, Statistics with R, as well. So I love this because it's a very fun little questionnaire, and it's also relatable for us because it deals with feeling anxiety about math and statistics, which is something that we all definitely feel sometimes, I think, when we're trying to learn new things. So it's 23 questions, and I actually have a copy of this questionnaire. This is also on Canvas, so you can kind of familiarize yourself with it. What I like is it's really set up like a traditional questionnaire that you would give in a regular research study. So it's a set of questions. They're all here, and they're all on a pretty traditional Likert scale from strongly disagree to strongly agree. Here on the scale represented as SD to SA. And we have 5 points. So there is a neutral point here. So there's strongly disagree, disagree, neutral, agree, and strongly agree. So all of these are measured on the same scale, and the coding basically runs from strongly degree equals 1, disagrees 2, neutrals 3, agree is 4. and strongly agree is 5. And as we look at this, all this stuff is broadly connected to statistics. So for example, statistics makes me cry. But it's also connected to things that are related to statistics. My friends will think I'm stupid for not being able to cope with SPSS. There's also some questions about math. I've never been good at mathematics. So as you can see, even though all these questions generally relate to the same concept, which is learning statistics or doing statistics, it looks like there might be some sort of specific subscales in there as well. And in fact, that's sort of how Andy Field designed this scale, is to have a series of subscales. And so this is just really good dummy data to use for our study of EFA. It's a pretty big data set. So we'll go ahead and glimpse this. 2,571 rows, 23 columns. I don't believe there's any missing data in this data set. Which is good. Often missing data can be difficult for exploratory factor analysis. So in this case, it's actually pretty nice that we don't have to deal with missing data in EFA. 23 columns, and everything is basically labeled. The questions are named according to this convention, Q, and then 2 numbers which suggest the number. So Q01 is question 1, Q02 is question 2, all the way to question 23. We can get the structure, use the structure command and the describe command to get descriptive statistics and labels. So that can be very useful. So here are the descriptive statistics. And again, the min and max here are all pretty much 1 to 5, which is what we're looking at. The means do differ a little bit, 2.5. In some places closer to 3, in some places actually below 2. So that's a pretty heavily skewed item. The median here being a 1. So that's really kind of pulling in that direction. Here, a few items above 3. Question 20 is pretty heavily skewed, which is also pretty interesting. So just, gives us a sense of where we are. And you can see the skewness and kurtosis here. Overall, though, it doesn't look too bad. None of these look too bad. But ideally, for EFA, you would want to remove items that were like seriously skewed, where there's just very little variability. But the more items you have in your scale, the less that tends to be an issue to have a few items like that. And then this is the structure command. So this gives us a sense of the items and the item labels, just to give us an idea here. And what I recommend too is also just looking at the items like this, if you know the questionnaire. So just doing a quick scan. Most of these things are phrased in a negative way, what we call a negative valence. The term valence kind of refers to whether something is negative or positive. It's like sort of the direction of the feeling. So statistics makes me cry. That's written negatively. My friends will think I'm stupid. Standard deviations excite me. That's a little different, right? So that's written in a positive valence. So we might pay attention to that one. Pearson's attacking me. I don't understand statistics. I have little experience. Computers hate me. I've never been good. Friends are better than me. Yep. So I'm just giving these a scan. People try to tell you it's easier to understand. I worry. Computers have minds of their own. They're out to get me. I weep openly at the mention of a central tendency. I slip into a coma. SPSS always crashes. Everybody looks at me. I can't sleep. I wake up under my duvet thinking I'm trapped under a normal distribution. I like that one. I think that one's funny. My friends are better at SPSS than I am. If I'm good at statistics, people think I'm a nerd. Okay, so first off, something jumps out at me, right? So this item, item 3, is the only item that's written in a positive valence. Okay, all these other items are written in a negative valence. And so there's some debate as to, in scale development, whether it's good or bad to do this. Generally, it's There's mixed advice. It's really hard to tell. And a lot of times it's very specific to the type of scale that you're working with. But the thing to pay attention to is if you have positively and negatively worded items that are part of the same scale, it's usually a good idea to reverse code those items so they're all sort of going in the same direction. Now, most modern software will catch this and will flip the scale for you. So it's not an essential thing that you do this, but it's definitely recommended. So that's something we need to think about. And down below, we'll make a note of that we need to sort of recode our SAQ clean item so that it kind of fits the pattern. Okay, so first of all, let's look at a correlation of all these items together. This is a good first step when you're looking at a scale, even before you do an EFA, because it gives you a sense of the extent to which you might have relationships between items, because you have to have relationships between your items in order to have a scale. If none of your items are correlated, or if they're correlated at a very low level, you may be in trouble from the outset. So let's do that first. That's our first step here. Create a correlation matrix with all of our indicators. Okay, we're back. Sorry. I thought that I was using a slightly older version of the code for this, and I was. So I caught it, and we're good. We haven't, it should look the same as what you have. The one thing that, that may have changed, you want to load in this core R package, which is a really good way of doing sort of quick correlations and things like that. So that's the only thing that has changed. So now we're down here again. We're looking at a correlation matrix for this SAQ data set, and it's very easy. I'm actually going to write this so I can use it later. So I'm going to create an object called core matrix, and that is going to be just running the correlate function on the entire SAQ data set. So we'll run that, and then we get a very nice message here. It says correlation is Pearson. So that's a standard Pearson product moment correlation, and missing are treated using pairwise complete observations. So what that means is there are different ways of handling missing data. Now, in this case, we don't have a lot, so it's not a big deal. But so pairwise complete observations means that the n can change for each paired observation. It uses all the observations that are present for that pairing. So it goes through and finds each pairing. So you might have 100 observation pairs here, but for another set of variables where somebody didn't answer, you may only have 80, and so it's going to switch around. You can always just do complete observations, and then it's going to get rid of anyone that has any missing data, which is another option. But the default is this pairwise complete observation. And then I can actually just print this to get a look at the correlations. Now, this does not have to be super scientific at this phase. What we want to look for, though, is that there are sufficient correlations in this data set to support a factor analysis. And so we're looking for correlations really in the 0.2 to 0.3, 4, 5, or even higher range. What we don't want to see is a lot of correlations below 0.2 or 0.1. That really suggests, and that could be positive or negative, by the way, because some of these scales may correlate positively or negatively with each other. But that would suggest that this is not a suitable data set for performing factor analysis. And so just looking at this, I see quite a few correlations at the 0.3 level, both positive and negative. Yeah, 0.4, 0.4, I'm gonna keep going here. 0.2, 0.5, 0.5. So yeah, in general, I'm seeing a good amount of sort of medium to medium large correlations. So that should help me with looking and finding a possible factor if it's there. So that's good. That's always a good first step. So now let's take care of this item number 3. That was one thing we made a list of we wanted to take care of. So again, this question is standard deviations excite me. It is scaled in the reverse direction. It's a positively valenced item. All of our other items are negative. So in order to do this, what we're going to do, We're going to create a reverse coded item. We're going to put that in our data set, and then we're going to remove the original. And we're going to call this new version saq.clean. So this is saq.clean. So we're going to start with saq, and then we're going to mutate, and we're going to call this q03r. This is a good convention to use. If you put the capital letter R or just the letter R in your item name, that just communicates to you that that is a reverse coded item. And that is going to be equal to 6 minus your original item, which is Q03. So this is a really useful trick for how to reverse code items. The trick is think about the highest value in the scale. In this case, it's 5, the top end of the scale, and add 1. And then you're going to subtract that new number minus the original score. So in this case, the scale goes from 1 to 5. And so to reverse code that scale, you're going to add 1 to the top end, which is 6. 5 plus 1, 6. And you're going to take 6 minus all the original scores. So if you think about this in your head, right, if I'm a 1 on the original score, on the reverse scaled score, I need to be a 5. And this accomplishes that because 6 minus 1 equals 5, and so on and so forth. So we do that here. That's this set of code here. And then we use that pipe operator again. I'm just going to select, and this is a cool trick. You can actually negative select. So you can select out items by putting the minus sign in there. So instead of having to list all the items that I want to keep in, I can just say I want to keep everything but the original item that was not reverse coded. So that'll give me a clean data set with a reverse coded item. We can double check. So using the glimpse function, so here is saq.clean, q03r. So the first 3 values were 2, 2, 4. And the first values of the original item are up here. They are 4, 4, 2. So they in fact are the opposites. And we've accomplished what we need to do. Okay, so now we're about ready to calculate a coefficient alpha. And so we'll start with, let's start with a subscale of these items, because as we already found out when we looked at this Andy Field questionnaire, it probably doesn't make sense to treat all 23 of these items as coming from the same scale, because just looking at them, they're getting at different concepts. Some are about math, some are about computers and other things. And so let's just select the items that have to do with computers. So those are 6, 7, 10, 13, 14, 15, and 18. So 6, 7, 10, 13, 14, 15, and 18. SPSS as well. I guess we could also do 19 has to do with SPSS, but it also has to do with friends. So I don't want to cause too much, make this too complicated. So I'm just going to keep just the items that has to do exactly with computers. And what you need to do in R, you need to create a little data set that just contains the items from your scale. So I'm going to call this computers, and we're going to start with our new clean data set. And then I'm going to select, and notice I've just listed the items here that pertain to computers. And when I run this, I now have a new little data set up here that is just the computer items. And then I can use the core R function to actually just get a set of correlations just of those items, which is pretty cool. So I'll make this a little bit bigger so I can see them all. So these are just the correlations associated with computers. So these should all be pretty close. We want these all to be, in like the 0.3, 0.2, 0.3, 0.4, 0.5 range or higher. And sure enough, they are, right? So all these correlations, and again, I'm just doing a scan here. I'm not, necessarily paying super close attention, but all these items are pretty closely correlated at about the 0.2 to 0.5 level. So that's a good sign. And then from here, we can calculate Chromebox alpha. The command is just alpha, but notice I do this little lazy loading technique where I force the computer to run the psych version of alpha. And the reason I do that is because alpha is a command or a function that gets used in a lot of different packages, including ggplot. And it is not Chromebox alpha and ggplot. It's some other command that has to do with how bright or how dense a picture is supposed to be. So I don't want that. So this is called lazy loading. So I'm actually forcing the software to use the psych version of alpha by putting that the name of the package and then 2 colons in front of it. It can be very handy sometimes when you have competing versions of the same function or same function name. You get a ton of output with the alpha package. Some of it is super useful. Some of it may not be all that terribly useful for our purposes, just sort of understanding the basics of alpha. But it still is pretty cool. So we get a nice summary of the of alpha just by going to the first page here, clicking all the way to the left, and we get an estimate of alpha, which is in the middle here. It's 0.82, so that's pretty good. And then we get a 95% confidence interval for alpha. That's really helpful too, and that can be really nice to report in a paper. You don't always get that. And with a larger data set, that 95% confidence interval is actually going to be pretty small, which is good, pretty precise. So this is a pretty precise estimate of alpha. Just a reminder of the kind of loose boundaries we're looking for with alpha. The general cutoff is 0.7 or higher. That is a very loose cutoff. It is not, if you have a bunch of reliabilities that are near 0.7, that's not great. Ideally, we want that at 0.8 or even a little bit higher. We also get what are called item reliability statistics or item drop statistics. Those are on the next slide. Those are very helpful. And then you get a non-missing response frequency for each item. So this is cool. So it shows you, first of all, how many of each item are missing. That's what this column miss is. So if you had missing items, it would tell you. And then you get a frequency. Since this is a Likert scale, this is the percentage or the proportion of responses that are in each one of these responses. So in other words, for question 6, 27% of people answered 1, 44 2, 13 3, 10 4, and 6% answered 5. So that's a left skewed item. Question 7 is kind of nicely normally distributed or close to it, and so on and so forth. We're not going to look at all these, but so this second data frame is just a nice measure of alpha. You get something called Gutman's G6, which is another measure of reliability. This is the average inter-item correlation, which is 0.4. That's pretty good. And the mean score across all items is 2.58. Standard deviation is 0.7. This is the median R as well. This data frame is pretty cool. It gives you a, I think this is item drop statistics. So this is alpha if the item is removed. And I believe this is item rest statistics. So this is the correlation between each item and the scale itself, but I'm not 100% certain that that's what all these are. The documentation for the psych package is very good and is a great resource if you want to go more into what that means. But for our purposes, alpha is 0.82. There's a lot more information you can get about this, but for our purposes. So what happens when we add an item that doesn't fit? So we're going to purposely add item 23. So before we did not have item 23. So item 23 is, if I'm good at statistics, people will think I'm a nerd. So here what we've done is we want to see what happens to alpha when we add an item that does not fit well. And ideally, we should see a change. So we're going to call this new little data set computers 2, and we're going to select all the items plus our new item. And here is our correlation. And I'm paying most attention to item 23, the correlation of item 23 with everybody else. And notice how it's not good, right? It's negative, it's basically 0. So there's very little signal of item 23 with these other items. And that's really good. And then when I add item 23 to my alpha and I look at how it changed, scroll up here to the top, alpha has dropped to 0.76. So it still would be acceptable, but is not as good. So this would actually be evidence of what you might call like divergent validity. So we've added an item that deliberately does not fit, and we show that it makes the fit of that thing worse. So that is a good, that's a good sign for this scale. You even get this little message, some items were negatively correlated and should probably be reversed. This is actually not the case. It's just a poor fitting item. It's not reverse coded. So sometimes the software tries to make some recommendations to you, but because it really doesn't know what's going on and it's trying to fix it for you. But in this case, it's just a bad item. All right, so last thing, I want to show you how to create a scale score, or how to score a measure using alpha. So let's say that we liked our original computer's measure that has 7 items. We got rid of that last crummy item that didn't fit very well, and we actually want to build a little scale score with this. So this would be equivalent essentially to taking the mean of all 7 of those items. That's essentially what we're doing, is we're taking the mean of all 7 of those items and getting one average score. This is called scoring the variable. And to do this in R, you have to first give the software a set of keys, and then create some scales based on those keys. So here is the key for computers. And this is cool because you can extend this and go, you can do another scale down here too if you want. But this is just the first one. So computers, and you list a key. It's basically it's a vector. In this case, it's a vector of item names that all fit together. So the computers variable is going to be composed of questions 6, 7, 10, 13, 14, 15, and 18. So we run that first, and that gets stored in our memory. And then we calculate our scale, and we score items according to our keys. And then this is data. This is the data set that we're using, this second command. And here we can actually impute, which is cool. That's what I like about the psych package. There are some options for imputing. Now, I don't think it's multiple imputation. I think it's single imputation. So it's imputing like the median or something, but still it's a cool option. It runs that under the hood for you, which is pretty cool. So that's called my scales. So you now have scales, and we can print this thing and get a look at it. So it just gives you a little summary. It gives you the alpha again. It gives you the standard errors. Gives you the average correlation, the median correlation, Gutman's reliability. So if you know you're going to score something, you can just do this and see what alpha is as well. And then non-missing response frequency, and so on and so forth. So you get a little bit of information there. And then you can then create a data table based on this. And you just use this command as tibble. So it converts these scores, which are now in sort of a list form, it makes them into a data set. So we run that. And here now over here on the side, I now have a something called my scores. I'm trying to make this a little bit bigger, but it doesn't want to. So now you see I have a score for everybody in this data frame, my scores. So 2.14, that's the average of the 7 items for the first person. 2.29, that's the average for the second person, and so on and so forth, which is really cool. So now I have all that. And then I can actually attach this to my old data set. So this is saq.clean1. And all I'm going to do is I'm going to bind columns. So I'm going to take that existing data set and I'm going to bind my new scores onto the end. So it's basically like tacking that new variable onto the end. So you old data set here, new data set there, and then I can glimpse this thing. And notice I now have 24 variables, and down here is my new scale score. So that's basically a scale score. We just calculated a scale score for the computers variable, which is pretty cool. All right. So this is definitely going to be a two-parter, right? Because this first part was just all about reliability and some basic kind of psychometrics and measurement and exploring properties of a scale. So just to recap, we use the psych package to examine correlations in our data set from our Andy Field Statistics Anxiety Questionnaire. We calculated an alpha for the computer's scale. We deliberately added an item that did not fit and saw that alpha went down, which is a good sign. And then we scored our scale using the my keys and my scales convention from the psych package, and then actually calculated an average scale score for every person. In part two of this video, we're going to actually perform an EFA, several kinds of EFA, and see how many other scales might be present in that questionnaire. We know the computer scale is there; it looks pretty good, but what else is there that we can use? So, all right, I hope you found this useful, and stay tuned for part two.